I'm Anuradha. In this video, I will explain how to design a 3D cup with parametric surfaces using MATLAB. The cup is formed by gluing together a paraboloid cup shape, about half a torus for the handle, and a hemispherical base. Additionally, a hemispherical saucer is also created for the cup. When the graph of a function z equal to f of xy is not easily expressible, we often use a parametric representation. Intuitively, we can think of this as starting with a flat piece of surface D, usually a rectangle or a disk in a plane, and then curving it in space to form the desired surface. The coordinates u, v are used to specify points on the initial flat piece of surface D. The curving of this piece in 3 space is equivalent to defining 3 functions on D for the 3 spatial coordinates as x of uv, y of uv, and z of uv. The mapping from uv coordinates to x of uv, y of uv, and z of uv, as given by this notation, is a parametric representation of the surface. The surface D spans the 2D space. Let us start with the main surface of the cup. The equation of a paraboloid as a function of z equal to f of xy is given by z is equal to x squared plus y squared. This is the surface of revolution of a parabola and can be parameterized by the equations x equal to r cos theta, y equal to r sin theta, and z is equal to r squared. Here theta varies from 0 to 2 pi and r goes from 0 to 2. The variables used for theta and r are u and v respectively, as shown in the code. Next, we come to the base of the cup attached to the paraboloid. A portion of the upper hemisphere represents this surface. The equation of a sphere is given as x squared plus y squared plus z squared is equal to r squared. And the parametric equations are as shown here. Here, r is the constant radius and theta varies from 0 to 2 pi, the longitude, and phi ranges from 0 to pi and is the co-latitude. We only take a portion of the upper hemisphere in our example, so phi varies from pi by 4 to pi by 2. The angles theta and phi are usually represented by u and v, as shown by the next section of the code. This is what the cup looks like now. Next, we come to the handle of a cup, represented by a part of a torus. The torus is a surface that has the shape of a doughnut. We can also think of this surface by rolling and bending the flat domain D into a tube and then bending it until the doughnut forms. The torus is a surface of revolution formed by the plane of a circle that revolves around one of the axes, in our case the z-axis. We can think of a circle that goes through the middle of the torus and lies on the xy plane. We can think of another circle that wraps around the torus and goes around the first circle. The second circle lies in the xz plane and rotates around the z-axis. Consider the unit vectors v1 and v2 perpendicular to each other and extend out from vector p. The vector d from the inner center of the torus to a point on the torus surface is given by the linear combination of orthogonal components v1 and v2. The vector p from the origin to the center of the torus is given by the ordered triplet r cos theta, r sin theta, 0. Before moving ahead, I want to show you something. For the last 28 days, roughly 5.4% of our viewers have subscribed to our channel based on our YouTube statistics. If you have not subscribed to our channel yet, we request you to subscribe now. Let us jump back to the video. The vector v1 is given by the triplet cos theta, sin theta, 0, and the vector v2 perpendicular to v1 is given by the triplet 0, 0, 1, pointing along the z-axis. The vector d sweeps through the angle phi between 0 to 2 pi. Therefore, the parameterization of the torus is represented by the vector a from the origin to an arbitrary point on the torus surface as a sum of vectors p and b. The following equations are given in the x, y, and z components here. The torus for the handle of the cup has its center at a point x0, y0 and z0 on the cup. Radius big R equal to 0.8 and small r equal to 0.25. Since it is only a part of the torus and oriented vertically, the angle varies from 0.4 pi to minus 0.66 pi. This is what the cup looks like at this point. Finally, we include a saucer, which is another parameterized lower hemispherical surface with a radius of 2, centered at 0, 0, 1.5, just underneath the cup. Its elevation angle varies from 0 to pi by 4, and the azimuthal angle ranges from 0 to 2 pi. This is how we can apply our knowledge of parametric surfaces to design an interesting object using MATLAB. This is what the final cup and saucer set looks like after running all the sections of the code. Thank you for watching this video. Do like this video. If you found it helpful, follow us on LinkedIn and Facebook and subscribe to our YouTube channel. Share comments with some exciting topics on which you would like to see more videos in the Fun with MATLAB series. Education is our future. MATLAB is our future. Happy MATLABing.